Okay. Okay, so 5.5, the last part of 5.5 is about orthogonal matrices. So I think today's lecture, compared to the last one, is going to be very low level, pretty simple stuff, because we'll be finishing up. Kind of the high point of this chapter was this business of least squares and connection to orthogonality and stuff, and now we're sort of like in the denouement, and then we'll go into the sixth chapter and start off slowly. Okay, so yeah, but the sixth chapter is quite becomes quite complicated. Okay, so it'll start off slow, but then becomes pretty deep. Okay, so get ready for it. Okay, so last thing in chapter 5 that we're going to do is this class of matrices called orthogonal matrices, and we're just going to make a few simple observations about them. Okay, so here's the definition. You have a square matrix. It's called orthogonal if its column vectors form an orthonormal basis of Rn. Okay, and it's orthonormal basis with respect to the standard dot product. Standard inner product on Rn. Okay. So the only thing that's sort of strange is that why do you call these things orthogonal matrices? It would sort of make more sense to call them orthonormal matrices, right? Because what you're asking is that the columns be an orthonormal basis. Okay, so there's some inconsistency. Just remember, if it's an orthogonal matrix means that the columns are all orthonormal. Okay, so one example is the rotation matrix, cosine, negative sine, sine, cosine. Right. As you see, these are orthogonal to each. The columns are orthogonal to each other, and they are all of norm 1. So this was counterclockwise rotation by theta. Some pretty straightforward properties of orthogonal matrices are one, this is sort of trivial, that a matrix is orthogonal if and only if, when you take the transpose of it against itself, then you get the identity matrix. Think about that for 10 seconds, and then nod your head to say that it's completely obvious. Right? Because you know that the columns are orthonormal, right? The columns are orthonormal, so Q1, Q2, blah, 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 Qn. These guys are all orthonormal to each other, right? And then you take the transpose of that. So you make Q, you make it like this now, Qn, right? And when you multiply them by each other, right, what are you going to get? You're going to get Q1 against Q1, that gives you 1. Q1 against Q2, that gives you 0. Blah, 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 do Qn, that gives you 0. Q2 against Q1 gives you 0. Q2 against Q2 gives you 1. And then against everything else, it gives you 0, right? Et cetera, et cetera, et cetera. So you're going to get 1s down the diagonal, and then 0s everywhere else, right? Because right, the ijth entry of QTQ is QI transpose against QJ against QJ, right? Which is going to be 1 if I equals J and 0 if I is not equal to J. Have I introduced this notation, the Kronecker delta notation? Maybe not. So this just means 1 if I equals J, 0 if I equals J. It's called the Kronecker delta notation. Just for your math culture, you may see it. Somebody else may use it. Okay, so what do you see? What we see is that Q is orthogonal if and only if Q transpose is Q inverse, right? Because you see QTQ is the identity matrix that tells you that the transpose is the inverse of the matrix, right? Okay. Other properties. So when is the game against Pomona and Pittsburgh?
So 1 o'clock at Pomona Pittsburgh. There's a faculty like
tomorrow.
Oh, tomorrow.
Tomorrow, yeah. And there's a tradition where like faculty, like staff, and like alumni and like students, they walk from the Bower Fountains to the field together at 12:40. If you want to join that, that's usually really cool.
Huh. Never heard of it. Never heard of it. I've been here for 9 years. Never heard of it. But maybe
A lot of people haven't heard of it. So.
Okay. Yeah, it's not impossible that I might participate.
That'd be awesome.
What? This is my way of getting into culture, getting into modern American culture. Yeah, just don't play Taylor Swift while we're walking.
I'll try not to.
Yeah, you see, I want to maintain my distance from culture to some degree. Yeah. No, actually, when I was in college, I actually bought a CD player with the intention of like trying to listen to modern American music, but I really didn't get into it. Yeah.
What type of music do you listen to then?
I don't listen to anything.
You just don't.
Yeah, I don't listen.
Wow.
Yeah. I don't have that.
Nothing?
Yeah, in fact, nothing.
Not even like classical mixed too. Yeah.
Do you listen to anything when you're in the car?
NPR, usually. Yeah, NPR.
Do you listen to like jingles on commercials?
I mean, I don't watch TV that much, so in some sense, no. But I mean, yeah, we didn't. Yeah, we just didn't have the habit in my family of listening to music.
You know, when you like started learning about the mathematics behind sound, did it like make you want to like listen to? Because didn't you say like last week that you learned that in undergrad?
Yeah. But no. I mean, but excluding this one period of time where I was trying to, get into modern American culture by listening to music. I borrowed CDs from friends and stuff. Asked for their suggestions on what to listen to. And like a good friend of mine gave me all these tapes, Steely Dan and stuff. The Eagles. Yeah. But yeah, I didn't really get into it. Yeah. Okay. So other properties of orthogonal matrices, and you might be wondering, why we care about these guys. They'll show up in the next chapter in a pretty crucial way. So other properties. One, if you have, using the standard inner product, qx against qy is the same thing as xy. The inner product of qx against qy is the same as the inner product of x against y for all y. Okay. And the second one, that the norm of qx is the same thing as the norm of x for all x. Why is the second one obvious? If you have the first one, why is the second one obvious? Mia.
Because it's the inner product of x against x.
Exactly. So just take x and y to be both x, right? If in the first one you take qx against qx, you're going to get qx against qx is x against x. In other words, the norm of this squared equals the norm of this squared, right? And so the norms are going to be equal. So 2 is an immediate consequence of 1. Okay. So we don't need to prove 2 if we have once we get 1. And the proof of 1. The proof of 1 is also not difficult. You say, well, look, qx, qy, by definition, is qx transpose qy. That's the definition of the Euclidean inner product. Right? You take the transpose of the first vector and then multiply it by the second vector. Right? This, you recall, was defined to be this. And then you say, okay, well, look, the transpose of qx is the same thing as x transpose q transpose qy. And then by orthogonality, this is the identity, right? QTQ is the identity, and so you get x transpose y, which is to say the inner product of x against y. So these are pretty simple, straightforward facts about the orthogonal matrices, but they have sort of interesting interpretations. Right? The second one says that Q doesn't change the norm of the vector. Right? If you're an orthogonal matrix, then you don't change the size of the vector. Okay. The first one says even better, that the inner product is preserved. Right? The inner product of x against y, if you hit each of those guys with a q, then the inner product is preserved. Right? But what does that tell you? That actually tells you that the angle between these guys is preserved. Right? Because the angle is defined in terms of the inner product. Right? So Q actually preserves angles, as well as norms. Right? You have 2 vectors, and you hit it with Q, then you know that those 2 vectors are going to end up with the same angle between them. Any questions about this? Questions? Okay, so that is it for chapter 5. Okay. chapter 6. Eigenvectors and eigenvalues. So, it's the definition. Let A be an n by n matrix, and lambda be some complex number. If there exists a vector v, a non-zero vector, such that AV equals lambda v, then we say lambda is an eigenvalue of A, and we say that V is an eigenvector belonging to A, belonging to lambda. Okay. So entering the next section. Henry, we're entering the next section, and here are the most important definitions for now. Okay, if there is a number and a vector, so that satisfying this relation that A of v equals lambda v, then we say that that vector is an eigenvector, and that its eigenvalue is lambda. Okay, so. If you have a vector and hit it with a matrix, there's no guarantee that it's just going to stretch, right? For the most part, it's not going to stretch. It'll give you something else in a different direction. But there are some vectors that are special for your matrix, right? When you hit them with the matrix, then they just get scaled. They just get scaled by some scalar. Those vectors are called eigenvectors, and then the scalars that scale the scaling scalars, the scaling numbers, are called eigenvalues. The scalars. Okay. So I'm going to give you a bunch of exercises. You can figure it out. You can figure out the beginning of the theory here. One, if lambda is an eigenvalue of A, then the collection of eigenvectors is a subspace. So the eigenvectors belonging to a particular eigenvalue form a subspace called the eigenspace. Eigenspace E sub lambda. Okay. So I'd like you to think about why that happens. Why is it true that if lambda is an eigenvalue, then all the eigenvectors corresponding to that eigenvalue are going to be a subspace, right? V such that JV equals lambda V. Okay, anyone have ideas on how to see that? Anyone have ideas on how to see that? There's sort of like the straightforward way to say, well, what do we need to do to show that something is a subspace? Right? What do you need to do to show something is a subspace? You need to show that the set is closed under scalar multiplication and closed under vector addition. Right? So you could do that. Right? Method one, you could say, well, look, let's say that v1 and v2 are both eigenvectors corresponding to that eigenvalue. Okay. And we want to show that v1 plus v2 is also an eigenvector. Right? Well, that's easy. You just say, well, let's take alpha times v1 plus v2, and you see that you get lambda v1 plus lambda v2. In other words, lambda v1 plus v2. And we also want to show that it's closed under addition. Second thing, say you have an eigenvector and a scalar, and you want to show that alpha v1 is in v lambda. Okay. Well, alpha v is in e lambda. Well, it's the same thing, right? Just multiplying by the matrix. Right? You pull this thing out, you end up with lambda v, which is lambda alpha v. Right? So a alpha v is lambda alpha v, and so it's closed under scalar multiplication as well. Okay, so it's trivial to see that it's that the collection of eigenvectors for a fixed eigenvalue are a subspace. But it's trivial, but it's actually interesting to do it in a different way, and it's more instructive to do it in a different way, which is to think like this: a vector is going to be in the eigenspace if and only if AB equals lambda IV. Where I is the identity matrix. Okay. That is to say, you are an eigenvalue, or you are an eigenvector if this happens, right? A minus lambda I times V equals 0. Right? That is to say, V has to be in the null space of A minus lambda I. The null space of A minus lambda I is the same thing as the eigenspace corresponding to lambda, right? So these are the same thing, so that this is a subspace, that's also a subspace.
Can you repeat the null space thing here?
Yeah, right. You are an eigenvector corresponding to lambda if this happens. This is the same thing as that, right? I move this to the other side, and I distribute out. And so what does it say? It says that V has to be killed by this matrix. Right? V is in the null space. V is in the null space of this matrix. Right? So the eigenspace corresponding to lambda is the null space of this matrix. In other words, right? And our question was, is E sub lambda a subspace? Well, the null space is a subspace, so this is a subspace. Exercise number 2. Lambda is an eigenvalue of A if and only if the determinant of A minus lambda I equals 0. Lambda is an eigenvalue of A if and only if the determinant of A minus lambda is equal to 0. Okay, so think about it for 1 minute and then tell me why. Are there no Pomona students in this class?
I know, Teresa's.
Oh, that's right, Teresa. Okay, so anyone have ideas? Why does this happen? If you're an eigenvalue, then the determinant has to be 0. Yeah, Elena.
If the determinant is 0, then a minus lambda I is non-invertible.
Mm-hmm.
And so then
0 is the same thing as saying that this is non-invertible. Mm-hmm.
So then that gives a minus lambda I times b equals 0, a non-trivial solution.
Right.
And then by what we did over there, b is an eigenvalue.
Right. So then B is an eigenvector belonging to there exist, I say this way, there exist eigenvectors belonging to lambda. And so lambda is an eigenvalue. Okay, does that make sense? Yeah? Anyone have questions? Okay, so these two simple observations actually give us a way of finding eigenvalues, finding eigenvalues and eigenvectors. So you see that all we have to do is look at the determinant of a minus lambda I, and find any lambda that will make the determinant of this thing equal to 0, right? So it boils down to then solving polynomials, finding roots of polynomials. So the above gives us a way of finding eigenvalues and then eigenvectors. Okay. So it starts off with definition, something called the characteristic polynomial. So if you have a square matrix, we call the determinant of a minus lambda I the characteristic polynomial of A. The characteristic polynomial of A. And what we see from our observation is that the roots of this polynomial are the eigenvalues of A. And I often abbreviate eigenvalues as just E-vals. I mean, it's not good. The eigenvalues. Okay. So right, so the game then, so somebody gives you then a matrix, 6, -4, 3, -1, and says, what are the eigenvalues? Right? Well, let's first find the characteristic polynomial. The characteristic polynomial is going to be the determinant of 6 minus lambda minus 4, 3, -1 minus lambda. The determinant, that's going to be 6 minus lambda times -1 minus lambda, and then plus 12. And turns into lambda squared minus 5 lambda plus 6, which is lambda minus 2, lambda minus 3. Okay, so that tells you that the eigenvalues are going to be 2 and 3. So eigenvalues are 2 and 3, right? And then to find eigenvectors, to find the eigenspaces, we just need to calculate them. So you say, let's find the eigenspace corresponding to 2, right? The eigenspace corresponding to 2 is just the null space of A minus 2I, right? The null space of this thing minus 2, so that's 4 minus 4, 3 minus 3, right? But that thing is, of course, equivalent to 1 minus 1. Right? That thing is row equivalent to 1 minus 1. And so all we need is that x1 and x2 be equal to each other. So this null space is the span of 1, 1. And you see, if you want to check it, you see that 6 minus 4, 3, -1 times 1, 1 is 2, 2. So you see that when you hit this vector or any scalar multiple of this vector by the A matrix, then you just get twice your vector back. It just gets stretched by a factor of 2. And so that's one eigenspace, and then we have another eigenspace, E3. E3 is going to be the null space of A minus 3I, right? Well, A minus 3I is going to be 3, -4, 3, -4. Right? So that tells you that x1 is going to be 4/3 x2, right? And so A3 is going to be the span of 4/3, 1. Any questions on how this sort of mechanical part of finding the eigenvalue and then calculating the eigenvectors, eigenspaces, right? You just use the fact that the eigenvalues are those things for which the eigenvalues are the roots of the characteristic polynomial, right? So you calculate the characteristic polynomial and you find its roots, and then using each of those guys, you calculate the null space. You calculate null spaces. Well, you've calculated null spaces many times, right? So that's straightforward. Okay. Okay. So. Okay. Some simple observations. Let A be an n by n matrix. And suppose that lambda is, say that lambda is an eigenvalue of A. Then, in fact, the complex conjugate of lambda is also an eigenvalue. So remember that if A is a complex number, right? So I'm sorry, if lambda is a complex number, A plus bi, right? I, the square root of -1. Okay. Then the complex conjugate is A minus bi. So what we're saying is that complex eigenvalues occur in pairs. Complex eigenvalues occur in pairs. You're always going to have the complex number and its complex conjugate are both going to be eigenvalues if your matrix is a real matrix. Okay. And the reasoning goes like this. You say, well, look, why? Well, let's say like this. The determinant of A minus lambda I is equal to 0. Right? Determinant of A minus lambda I is equal to 0. Right. Now, this determinant is just some complex expression. So I'm going to put complex conjugation over everything. It's just a number, in fact, right? This thing on the left is just some number, right, equaling 0. In fact, it's 0. I'm going to put complex conjugate on both sides, right? The complex conjugate of this is going to be equal to the complex conjugate of that, right? So that's, of course, the complex conjugate of 0 is still 0. Okay. But what is the complex conjugate of the determinant? What's the complex conjugate of the determinant of this thing? The complex conjugate of the determinant of a matrix. Well, that's going to be actually the determinant of the complex conjugate. Okay. If you think about it, that's going to happen, right? And so what you get is that, and the determinant of, I'm sorry, the complex conjugate of a difference is always going to be the difference of the complex conjugates. And so I can actually split this one up too. But A is a real matrix. And when you take the complex conjugate of the matrix, of a real matrix, nothing happens, right? Because complex conjugate, if your number is real and you take its complex conjugate, you just get that number back. Because the complex conjugate reverses the imaginary part. But if your number is real, then reversing your imaginary part doesn't do anything. So the determinant, the complex conjugate of this real matrix is just going to be the matrix itself. And so we end up with this. Okay, and so what that says is that the determinant of A minus complex conjugate of lambda I is 0. Right? In other words, lambda I is an eigenvalue. Right? So this equals 0. This equals 0. So lambda I, lambda conjugate, is also an eigenvalue. But we needed A to be, we really used the fact that A was a real matrix here. Okay. Any questions about that? Questions about that? Okay. Second and probably last observation for today. So we know that these guys occur in complex conjugate pairs. If you have such a pair, if lambda and lambda conjugate are eigenvalues, then something is an eigenvector if and only if its complex conjugate is an eigenvector corresponding to the complex conjugate of the eigenvector. Yeah, what this basically says is that the eigenspace, if you take your eigenspace corresponding to, if you take the lambda and take the complex conjugate of everything in there, what you get is the eigenspace corresponding to the complex conjugate eigenvalue. Right? That these eigenspaces are complex conjugates of each other. Okay, but this sounds pretty sophisticated, but it's just a simple fact. You say, well, look, if V is an eigenvector corresponding to lambda, that's the same thing as saying that AV equals lambda V. Right? And then you complex conjugate everything. AV equals lambda V. Right? That's to say A V bar equals lambda bar V bar. That's the same. And a bar is that, so you end up with this. Okay, so nothing. It's really a nothing observation. Any questions about this thing? It's pretty straightforward. The next time we're going to start off with the following not so simple observation about the product and sum of the eigenvalues. Okay, it will say that if you have a matrix and lambda 1 through lambda n are the roots of the characteristic polynomial, yeah, possibly repeated. I mean, some of these guys might be the same. Then the determinant of A actually turns into, if you take the product of all those roots, the product of all those eigenvalues, then that actually gives you the determinant. And the trace of A turns out to be the same thing as the sum of all the eigenvalues. Do you remember what the trace is? I don't remember if I think we may have seen it in a homework problem. It's the sum of the diagonal elements. It's the sum of the elements down the diagonal of your matrix. So what we're going to see is that the determinant is actually the product of all the eigenvalues with multiplicity, you know, counting doubles if there are doubles. And the trace, the sum of the elements down the diagonal, turns out to be the sum of the eigenvalues also. Which should be a pretty mysterious statement at this point. Yeah. Like, why does that happen? I mean, it would sort of make sense if your matrix looked like this. If this were your matrix, yeah, suppose this were your matrix, then certainly the determinant is going to be the product, and the trace is going to be the sum, right? But that's not what we're saying, right? Your matrix is some other matrix. Right? Your matrix is some other matrix, and what we're saying is that the determinant of this matrix is the same as the determinant of this, and that the sum down the diagonal is the same as the sum down this guy's diagonals. So that should be sort of mysterious, but maybe take a look. The proof is a little bit tricky, so you might want to take a look at it before class. Okay, see you guys on Monday.